SwayamPrabha. Digital India. Educated India.
We have been discussing approximate methods for vibrational analysis as a build up to developing the finite element method. So, in today's lecture we will be talking about what is known as Rayleigh Ritz method and method of weighted residuals. Before we get into the details, we will quickly recall what we have been doing. Exact solutions to partial differential equations with inhomogeneous coefficients is in general not possible even for linear systems. So, approximate solutions are invariably needed. Right now we are discussing approximate solution strategies for finding natural frequencies and mode shapes, and we will now move to forced response characteristics as well, and this discussion is a prelude to the development of finite element method. So, we introduced during the previous lectures a quantity known as Raleigh's quotient, and for a discrete multi-degree freedom system we showed that Raleigh's quotient u is a n cross 1 vector where n is a degree of freedom, is given by u transpose ku divided by u transpose mu. This quantity is known as Raleigh's quotient. This has units of radian per second whole square, and if this vector u coincides with the nth eigenvector of the system, then Raleigh's quotient becomes exactly equal to the nth natural frequency of the system, or the nth eigenvalue, which is square of the nth natural frequency. We can also show that the Raleigh's quotient is bounded between the first eigenvalue and the last eigenvalue. Moreover, we have also shown that if the vector u is in the neighborhood of the true eigenvector phi n, that is phi n plus epsilon y, then we can show that the Raleigh's quotient will be in the neighborhood of the natural frequency with an error which is order epsilon square. So, we can also show that as we vary u, R of u reaches stationary values in the neighborhood of true eigenvectors of the system, and it reaches its minimum value when u coincides with the first eigenvector. This is known as Raleigh's principle. The main application of Raleigh's principle is to estimate with simple approximations to the mode shape, the first mode shape, the first natural frequency. That is the main application of Raleigh's quotient. Now, this is for discrete multi-degree freedom systems. For a continuous system like axially vibrating bar or Euler or Bernoulli beam, we have shown that Raleigh's quotient is now a function of the trial function phi of x defined over 0 to L, and for a axially vibrating rod it is given by this, and for Euler Bernoulli beam it is given by this. For distributed parameter systems, the Raleigh's quotient provides a bound as shown here. There is no upper bound because for distributed parameter system the highest natural frequency tends to infinity. Therefore, we can't place a bound on Raleigh's quotient as well. So, again if as we vary phi of x, whenever phi of x coincides with the true eigenfunction of the system, then Raleigh's quotient corresponds to the true eigenvalue of the system, which is square of the natural frequency, and again this function reaches a stationary value whenever phi of x is in the phi of x reaches is in the neighborhood of the true eigenfunction, okay, and it takes a minimum value when phi of x is equal to the first eigenfunction. Now, some illustrative examples. Suppose we consider a 3-degree freedom system with k as shown here, m as shown here, and let us assume that the kind of problem that we wish to solve is as follows. For this system shown here, the first eigenvector is obtained as shown here 1.13, 1.63 and 1.78, and the first natural frequency as 4.15 radian per second. Now, due to a design modification of the the third mass is changed by about 15%. That means, this mass I increase by 15%. Now, the question is how to estimate the change in the natural frequency. Exact analysis, but that is not what is intended here. We wish to find an approximation to the change in the natural frequency. So, for this system, for the modified system, the mass matrix is shown here. So, this M3 is increased by 15%, that means this will go to this, and k remains the same as it was earlier. And what we will do now is, since the first eigenvector is already given to us, we will use this as the trial vector. So, and compute the Raleigh's quotient. So, for this value, for this eigenvector and with the modified mass matrix, the Raleigh's quotient turns out to be 16.10, from which I get the modified natural frequency as this. Now, so therefore, the estimate of the change in natural frequency is about 3.3%. So, a 15% change in mass results in about 3.3% change in natural frequency as per this formulation. For sake of reference, we can note that if you were to do an exact analysis of the modified system, you will get the first natural frequency as 4.0121 radian per second. So, this is a one simple situation where Raleigh's quotient can serve some useful purpose. Now, an example for a distributed parameter system. So, here I am considering a simply supported beam which carries a point mass m, and also it is mounted on a spring k. If this k is 0 and m is 0, we know the exact solution to the natural frequencies of this system. This is amenable for exact solution, that is well known. Now, the objective is to find characterize the first natural frequency of the system using Raleigh's quotient. So, we write the expression for the potential energy and the kinetic energy. This is the strain energy stored in the beam, and this is the energy stored in this spring. This is at x equal to b, therefore, this is half k v square b comma t, and kinetic energy will be the kinetic energy stored in the beam, which is this, plus the kinetic energy stored in this point mass, which is half mv v dot square at a comma at a x equal to a. Now, if the system undergoes normal mode oscillations, it is understood that the form of the oscillation is as shown here. That means, all points on the structure vibrate harmonically at the same frequency. So, the form of the solution will be phi of x into cos omega t minus alpha. So, now I substitute that and compute the kinetic energy. So, we can get the kinetic energy as a term inside the brace and cos square omega t minus alpha, and similarly for this is potential energy, this is kinetic energy, which is given here. Now, the maximum value of V of t is reached when this cos square omega t minus alpha takes its maximum value, and that is 1, because cosine function is cosine function lies between plus minus 1. So, cos square omega t minus alpha would lie between 0 and 1. So, similarly t of t, the maximum value will be taken when this sin square omega t minus alpha is 1. So, the maximum potential energy is given by this, maximum kinetic energy is given by this, and since the system is conservative, these two quantities must be equal to each other, and this leads to the definition of the Raleigh's quotient as shown here. Now, to proceed further, we have to make a choice on phi of x. This is the definition of Raleigh's quotient for the problem. Now, we have to make the choice for the Raleigh's quotient. What we can do is, as I pointed out already, if this mass is not there and if this spring is not there, we know that sin n pi x by L for n equal to 1, 2, 3, 4 etc. are the set of exact eigenfunctions. Now, for this case, we can as well take the trial function to be sin pi x by L, or I can take a polynomial like x into L minus x, or I can apply a UDL on this beam and find out the deflected profile and use that as the trial function. So, there are many options that we can follow. Now, the choice of this phi of x determines how good this Raleigh's quotient is as an approximation to the first natural frequency. No matter which choice you make, this inequality will be honored. That means, R of Raleigh's quotient will be always greater than or equal to the square of the first natural frequency. So, now suppose if you take phi of x to be sin pi x by L, now you get the natural frequency to be given by this. You can carry out this integration, they are very simple, you will get this. Now, clearly when k equal to 0 and m equal to 0, the natural the frequency should revert back to the exact solution, because the mode shape is exact in that situation. So, that indeed happens, we get for k equal to 0 and m equal to 0, the square of the natural frequency as this, which leads to the estimate of first natural frequency to be this. This is in fact pi square 1 by L square E I by m, which is the exact solution. Now, on the other hand, if you now take the trial function to be x into L minus x. So, it satisfies the geometric boundary condition at x equal to 0 and at x equal to L, but if you compute the second derivative phi double prime of x, you will see that this trial function does not satisfy the natural boundary condition, that is the bending moment at the supports is not 0 according to this trial function, but this does not matter in this application of the method, because to compute Raleigh's quotient the highest derivative of phi that I need is phi double prime. So, there is no problem here as far as application is concerned. So, if I do that this integration is straightforward and I get the Raleigh's quotient in this case to be this, and if in this case if k equal to 0 and m equal to 0, if you compute you will get this as 10.95 into this quantity, which is higher than 9.87 into the same quantity that we got when we use the exact solution. Now, for k not equal to 0 and m not equal to 0, to gain an understanding how this method works, we can assign some numerical values. So, I have taken span to be 3 meters, Young's modulus to be 210 gigapascals, so density A and B, and beam cross section being rectangular with this width and depth, and mass point mass is half of the beam mass, and stiffness of the spring is this. And if I now use two trial function phi of x equal to sin pi x by L, and phi of x is x into L minus x. For the case when m equal to 0 and k equal to 0, we get the exact solution is possible, that also I have tabulated, and this trial function now as I already said coincides with the exact solution. Therefore, we should expect the exact solution which is as it should be. For x into L minus x I get 364.63 as an estimate for 328.51. So, this is still a bound, nothing wrong, but this is a, as you can see this may not be an acceptable approximation. Now, for non-zero values of m and k, this solution turns out to be 270.31 and this gives an answer 2.97.42. Now, we do not know the exact solution. So, now the question now arises, if you are using Raleigh's quotient, how do you improve the result? Suppose if you had started with this, you have got 297.42, and by some logic suppose you move to this shape function, you get a much better answer, right. But this is fortuitous, you happen to know the exact mode shape, therefore, you are able to get this a much lesser value for Raleigh's quotient than a simple function like this. But how do we systematically lower the Raleigh's quotient, right. So, that takes us into the next question, that is how to lower the value of Raleigh's quotient. This leads to the method known as Rayleigh Ritz method. Now, the main objective of Rayleigh Ritz method is to lower the value of Raleigh's quotient. So, let us start with Raleigh's quotient for the beam. I am using the beam as an example, an inhomogeneous beam with flexural rigidity varying in space and mass per unit length varying in space. What we do is we expand the trial function in a set of linearly independent functions psi n of x. Okay. These psi n of x are taken to be known functions, whereas these a n's are unknowns. So, the psi n are a set of known linearly independent functions which satisfy all the boundary conditions. Let us start with this and let us revise this, revisit this question as we go along, but for a moment we will assume that it satisfies all the boundary conditions. Now, a n's are a set of unknown constant which need to be determined. Now, the strategy is now as follows. Now, by introducing a series representation like this in my definition of Raleigh's quotient, I have introduced a set of undetermined parameters. So, I have a handle now to lower the Raleigh's quotient. So, the strategy that we will take is we will minimize Raleigh's quotient with respect to these unknown coefficients. So, select a n such that this Raleigh's quotient is minimized. So, that leads to, suppose after I represent phi of x in terms of these n parameters, now this r now is a function of n parameters, it is no longer a functional, it is a set of n, a function of set of n parameters, let us call it as capital omega square, and this is written like this. Now, the condition for optimality is dou r by dou a I must be equal to 0 for I equal to 1, 2, 3 and n. So, this simple calculation can be done as follows. We can call this denominator as a and numerator as b. So, I am asked to find now dou r by dou a I. A is a function of a1, a2, a3, b is a function of a1, a2, a3. Therefore, I use the rule of differentiation. So, I get 1 by b square where b is the denominator into b into dou a by dou I minus a into dou b by dou a I, that must be equal to 0. Now, since I am equating this to 0, this b square is inconsequential. So, I can forget that. So, I get the condition for optimality to be this. Now, if I divide in this case both sides by b, I get a by b. A by b is nothing but omega square. So, this will be therefore dou a by dou a I into omega square dou b by dou I equal to 0. So, that is what we are doing here for now if I want dou a by dou a I have to differentiate this with respect to a I. A I is one of the terms here. So, you differentiate, this becomes 2 into this summation into psi I double prime of x. So, that is what is written here, and this 2 is because of this 2. Similarly, I get the differentiation with respect to the denominator, this is equal to 0. Now, I divide by b and I get omega square, and this I have to do for I equal to 1, 2, 3 and n. So, it leads to capital N number of equations. So, we denote now k I n as E I psi n double prime psi I double prime dx, and m I n as a term here as m of x psi n psi I x dx. Now, consequently, this equation can be written as n equal to 1 k I n a n minus omega square n equal to 1 m I n a n equal to 0 for I running from 1 to n. So, this is a set of capital N number of equations in the unknowns a 1, a 2, a 3, a capital N. So, this can be put in the matrix form, I get k a is equal to omega squared m a. So, this k is a n cross n, capital N cross n square matrix, m is a square matrix of the same size, and if you see here the expression for k I n and m I n, k I n is same as k n I and m I n is same as m n I. That would mean k and m are symmetric n by n matrices. So, this A is n cross 1 column. So, this k A equal to omega squared m A represents an algebraic eigenvalue problem. K we call it as generalized stiffness matrix, m as generalized mass matrix. K is symmetric, m is symmetric. Now, actually to get a representation like this, we should, since phi is a function of x, we should really be writing this as n equal to 1 to infinity. Now, since we are terminating this expansion at lowercase n equal to capital N, this would mean a k equal to 0 for all k greater than n. So, to achieve this we need to supply external forces to the system which increases the stiffness of the system. Consequently, the natural frequencies get overestimated. Now, we can achieve some computational simplicities if we select psi n of x to be orthogonal with respect to m of x as shown here. This is Kronecker delta function. Then what happens is this generalized mass matrix will be an identity matrix. So, in which case the eigenvalue problem will be the standard eigenvalue problem k A equal to omega squared A. Now, once you find the eigenvalues, you will get associated eigenvectors, and using those eigenvectors we can also construct the approximation to the eigenfunctions, which is phi k of x a k n summation over a k n sin of x. So, this method the basic aspiration was to lower the Rayleigh's quotient, but as a byproduct we actually what we have done is we have ended up with discretizing the system as a n degree of freedom system, and from that we are able to get approximations to not only the first natural frequency, but up to the capital N number of natural frequency and associated mode shapes. So, this is a byproduct of the method. So, this is a way of, this can also be viewed as way of discretizing a continuous system as a multi-degree freedom system, discrete multi-degree freedom system. Now, we will examine this solution bit more carefully. Suppose if I retain only one term, so I get a single degree freedom approximation. So, from that model I can get only an estimate to the first natural frequency. On the other hand, if I now retain 2 terms, I will get a 2 degree freedom approximation. Therefore, I will get approximation to the first natural frequency, and a new information that I will get is an approximation to the second natural frequency. Similarly, a 3 term expansion will lead to estimate of first and second natural frequency and also the third natural frequency. So, so on and so forth. So, a capital N degree of freedom system will give approximation to the first n natural frequencies. Now, we can show that if omega n are the true but unknown natural frequencies, these omegas, that is this omegas that I am showing here, have this bounding property. That means, these eigenvalues converge from the above. So, I will show you the numerical example. What it means is, as the degree of freedom increases, the natural frequency approaches the true natural frequency from above. How do I show that? Maybe we can work through this example once again. Suppose the same problem, a beam with a point mass and a spring, and the numerical data as we had used in the previous example. So, what I will do is, now I will take the trial function to be a linear combination of sin n pi x by L. Okay. Now, just again let us quickly recall, when k equal to 0 and m equal to 0, sin n pi x by L is the exact nth mode shape for the system, nth eigen function of the system. So, with k and m not 0, this is no longer the exact solution, but we can use that as a trial function. So, that is what we are doing. Now, we will get now the eigenvalue problem as shown here, where Kij we can work through the steps and show that Kij is given by this, Mij is given by this, and delta Ij again is the Kronecker delta that we can get. Now, the fact that for the first 2 terms here we are getting Kronecker delta is not surprising, because sin of x is the exact mode shape for the beam problem. So, sin of x is orthogonal to Ei of x, that is sin double prime into psi k double prime Ei of x integral 0 to L dx is Kronecker delta function. So, that is known. So, that is why we are getting Kronecker deltas here, but of course, Kij and Mij are not diagonal because of these terms involving the discrete spring and the point mass. Now, if we now take only one term, I get 270.309 as the approximation. If I now take 2 terms, I get now for the first natural frequency an estimate of 266.024 and an estimate for second natural frequency as well. So, 3 terms I get a slightly different answer for first natural frequency and a new information on third natural. So, so on and so forth. If you continue, I have listed here for first 5 modes. So, for a 5 degree of freedom system, these 5 numbers are respectively the estimates of the first 5 natural frequencies. Now, if you look at this column, you can see that it is converging from the top. Similarly, this is converging from the top. So, this happens for all the eigenvalues. So, this is one of the properties of Rayleigh Ritz method, provided you use linearly independent trial functions. This is a very useful property. Now, we have been talking now till now about finding approximations to the natural frequencies and mode shapes, but we could as well ask the question now, how to get an approximation to the forced response itself. So, how do we approach that? So, there is a class of methods known as method of weighted residuals. So, for purpose of illustration, I will consider again a beam problem, a beam with inhomogeneous flexural rigidity, mass per unit length and damping properties driven by a distributed loading f of x comma t. Now, let us assume that initial conditions are initial displacement is this, initial velocity is this, and appropriate boundary conditions involving geometric and natural boundary conditions have been specified. It could be simply supported cantilever, fixed, so on and so forth. Now, in this class of methods, the starting point is we assume the solution to be represented as a series n equal to 1 to capital N, a n of t, phi n of x. These a n of t are the unknown functions of time to be determined, we do not know that. These are called generalized coordinates. This phi n of x are the known trial functions. Now, what conditions these should satisfy, we will see as we go along. So, what I do now, I substitute this assumed form of the solution into the governing field equation, and if I substitute here, I will get this is the field equation and this is the assumed solution. Now, I have substituted here, what happens is this equation will not be exactly satisfied. We do not expect that this equation will be exactly satisfied and we will be left with an error. If indeed this is an exact solution, this error will be 0 for all x and t, but that is not going to, I mean that is not the situation that we are discussing. So, there will be a error, or this is also known as residue. For the exact solution, this error is 0 for all times and for all x in 0 to L. For an approximate solution, as I said, this is not so. Now, what is the strategy now? We have to still select a n of t, which are not known. The strategy that we follow is we select these unknown functions such that a specified measure of the total error is minimized in some sense. We can't expect E of x comma t to be 0 for all x. Suppose you fix a time t, and if we can find a n so that E of x comma t is 0 for all x, then that is the exact solution. But that is not what we are doing. We want to minimize a measure of this error, a measure of total error, but this measure itself has no unique interpretation. There is no unique sense of minimization, because there is no unique sense of criterion of total error and how to minimize it. Depending upon the sense of minimization, we have different methods. Method known as method of least squares, what we do is, this is the residue which is given as shown here, and we define what is known as total mean square error, which is epsilon of t, which is integral 0 to L e square of x comma t dx. We are squaring because we do not want positive and negative errors to cancel. So, we could have taken the integral of error over 0 to L, but if for certain parts of the beam error is positive and for certain other parts of the beam it is negative, we get a false impression that total error is 0. So, we square that and find the total error. Now we select a n of t, so that this epsilon of t is minimized with respect to a n for n equal to 1 to n. So, this leads to a set of capital N number of equations for the generalized coordinates a n of t. So, if you do that, so you will get 2 e dou e by dou x t dx equal to 0, that 2 is irrelevant because on the right hand side is 0. So, this is for 1 to n. So, this can be written as in general w n x comma t e of x comma t dx equal to 0, where w n x comma t is this function, okay, for n equal to this. Now, if you write all these equations, you can show that the resulting equation will be of the form m a double dot plus c a dot plus k a equal to p of t. This p of t will be of course integral of f of x comma t multiplied by this quantity and integrated 0 to L, and that need not have units of force. This function need not have units of force. So, the interpretation of these matrices also needs to be carefully done. They need not have the traditional units, and they may or may not be symmetric. Okay. So, that also we have to bear in mind. Now, let us see if I can find the expression for that the weight. So, what I am supposed to find is dou e by dou a n, right. So, dou by dou n of the residue, you can see that it is given by E I phi n double prime of x, the entire thing differentiated twice. This is the weight function in this method, that is a W n. So, the criterion for minimization of the error is given by this for n equal to 1 to n, and this is independent of time. So, W is, although I wrote it as x comma t, it is actually W of x only. So, this is M I j is given by this, C I j is given by this, P j is given by this, and K I j is this. So, you can see here M I j is not same as M j I, and K I j is of course symmetric because of the way these terms appear here, but it is not true for C I j, and P of t is may not have units of force. Okay. So, these are some issues that you may have to bear in mind when you are solving and interpreting this solution. In another strategy, what is known as method of collocation. What we do is, we again look at this residue, which is as before E of x comma t, which is this. We select this a n of t such that this error is 0 for a given t, this error is 0 at n chosen points along the beam. That means, I select x1, x2, xn and demand that at all these capital N number of points the error is exactly equal to 0. So, that requirement leads to capital N number of equations for the generalized coordinates, and that is the governing equation. Now, we can see that this is equivalent to taking the weight function to be a Dirac delta function. So, this is same as Dirac delta of x minus xn E of x comma t dx equal to 0. That means, the statement that E of x of t is 0 for xn equal to xn n equal to 1 to n is equivalent to this. Now, that is we can write this criteria as integral 0 to L w n x comma t. It is actually w n of x because there is no time here. This time can be deleted from this E of x comma t dx equal to 0, where w n is this. Now, this leads to again a set of ordinary differential equations which are coupled, and you can verify that these matrices will be unsymmetric, non diagonal, and this will be the equation of motion. Now, the problem with this method is, although the error is exactly 0 here, we do not have an idea how small or large the error is at an x which does not coincide with any of these x. So, this we do not get any idea on that. So, you have to be careful in using the collocation method. So, the details of the matrices are obtained here. So, this is the criterion for finding the generalized coordinates, and Mij turns out to be mxi phi j xi, and which is obviously not equal to mji, and similarly Cij is obtained as this and Kij is obtained as this. This is again not symmetric. Pj of t is f of xj comma t. So, this is how we get this equation. A modified version of this is what is known as subdomain collocation method. It is somewhat similar to collocation method, but the criteria is that we again divide the beam into capital N number of segments, but instead of demanding that at all these points the error is 0, we demand that over each of these segments the average error is 0, that is the total error over this segment is 0, total error over this segment is 0. So, I write this as integral xn minus 1 to xn E of x comma t dx equal to 0 for n from 1 to capital N, where x naught is 0, xn is capital L. Now, this can be rewritten as integral 0 to L Wn of x comma t, it is Wn of x E of x comma t dx equal to 0, where Wn is a box function written in terms of Heaviside step function. So, for this method subdomain collocation method, the weight function is a box function. Okay. So, this is a modified version of collocation method. There is another method known as Galerkin's method. This is going to be used often in our course. Here the idea is the weight function is selected to be the trial function itself. So, we are expanding V as in terms of phi n of x, and the weight function we take it as phi n of x itself. So, this leads to, that means the error is orthogonal to the trial functions. So, this leads to capital N number of equations, and we will see now what is the form of this equation, but from this statement you can see that we are going to get a set of n ordinary differential equations. So, what exactly happens here? Again let us start with the residue term. So, the Galerkin statement is this, and you can see here if you implement this, Mij will be m of x phi j of x dx, and this is mji. Cij is c of x phi I of x phi j x, this is cji, and kij is actually this. We can see what happens to this is the fourth derivative present here, and this is there is no derivative on this. We will see what happens to this term, but in any case this is the kij. Now, Pj of t is the forcing function. Now, what happens to kij? So, now this if you integrate by parts, you do it twice. So, upon each integration one of these derivative passes on to the weight function. So, after you integrate by parts twice, you get the integral 0 to L, we will have phi I of double prime of x phi j double prime of x. Now, if we take all trial functions to satisfy all the boundary conditions, then these quantities inside the brace, these two terms will be 0. because these encapsulate the class of admissible geometric and natural boundary conditions, and this will be 0, and we get Kij to be given by this, and Kij in this case is symmetric. So, in this method I am getting again equation of the form Ma double dot plus Ca dot plus Ka equal to P of t, but the advantage is MCK are symmetric, and there are further advantages, I will come to that as we go along. It is something to do with the demands on differentiability of the trial functions. Now, how do we get initial conditions? We have got now the governing equation for the generalized coordinates, we need to find A of 0 and A dot of 0. So, how do we get that? So, this is the assumed solution V of x comma t is A n of t phi n of x, therefore, at t equal to 0 I get this displacement, at t equal to 0 the velocity is given by this. So, the unknowns are A n dot of 0 and A n of 0. So, this in collocation method again we can demand that the error is 0 for at n points, and I get these equations for I equal to 1 to n, and you can solve this equation to get the required initial conditions. Similarly, this is the equation for the initial displacement, initial velocity. In the least squares and Galerkin methods, A of 0 is given by the inverse of this matrix into the integral over the initial condition as shown here. Okay. So, this again requires some effort to evaluate the initial conditions. So, let me summarize what we have talked now. There is a least squares method, collocation method, Galerkin's method, subdomain collocation, and Petrov-Galerkin. There is one more thing known as Petrov-Galerkin, I did not talk about it. Here it is similar to Galerkin technique, except that the weight functions are taken to be another set of psi n of x. This psi n of x is different from phi n of x, that is that technique is known as Petrov-Galerkin. So, in all these approaches you can see here one of the common term that is present in all these expressions is E of x comma t. What distinguishes one method from the other is what multiplies this residue term in the integrand. For least squares it is this, for collocation it is this, for Galerkin it is phi n of x, for subdomain collocation it is this box function, for Petrov-Galerkin it is sin of x. So, all these methods nevertheless can be put as a weight function into a residue equal to 0 for n equal to 1 to n. So, this class of methods is known as method of weighted residues. Now, to implement these methods there are certain choices that we have to make. First, set of n trial functions, then a set of n weight functions we have to choose. Now, issues when you are selecting trial function or the weight function, order to which the functions need to be differentiable and how well they satisfy the boundary conditions, and also how many terms need to be included. So, we will revisit these questions, but bear in mind these questions need to be addressed. So, the general format is we have the field equation and we assume this solution, and after applying the method of weighted residual in any one of this form I get this set of equations. Of course, the meaning of M, C, K and P would be different depending on which method you have used. So, what does method of weighted residuals achieves? A partial differential equation governing the behavior of a continuous system has been replaced by an equivalent set of ordinary differential equations which are initial value problems with a view to obtain an approximate solution. So, that is what we are doing. So, this is a way of discretizing an infinite dimensional system by a finite dimensional system. So, in fact, finite element method also achieves this, but in a somewhat different way as we will see shortly. Now, the trial functions, there is a scheme of classifying trial functions depending on the extent to which they satisfy the boundary conditions. See, this is a field equation, for example, free vibration problem, this is a field equation, and we have boundary conditions, one on geometric quantities, another one that is the force quantities, the bending moment and shear force, call it as set 1 and set 2. So, in normal mode oscillation this is a solution that we assume, and this is the eigenvalue problem that we get. Now, we say that a trial function is admissible if geometric boundary conditions are satisfied. we need not have to satisfy the natural boundary condition nor the field equation. By field equation I mean this. By comparison functions we mean those trial functions which satisfy both geometric and natural boundary conditions, but the field equation is not satisfied. On the other hand, an eigen function is an exact solution to the problem, therefore, it satisfies the geometric boundary conditions, natural boundary conditions as well as the field equation. So, as you see here, the least that we should expect from a trial function, that it should be admissible. Okay. So, we will see what is the implication of this as we go along. It is also tied up with the requirements on differentiability of the trial functions. So, if a function is admissible, the requirements is much less, whereas if it is comparison function where you need to satisfy conditions on bending moment and shear force, the requirements on differentiability increases and the class of functions that we can select shrinks. So, ideally we would like to deal with admissible functions, so that we have a huge class of selection functions to select from. As we go in this direction, that choice of trial functions narrows. Now, let me just go back to one method, the methods one by one, and see what type of requirements each method imposes. In Rayleigh's quotient method, I need to evaluate only the second derivative of the trial function. So, they must be admissible, okay, and possess non-zero derivatives at least up to the second order. Okay. In Rayleigh Ritz method, again the trial functions need to be at least admissible and possess non-zero derivatives up to the second order, because if you see the implementation of Rayleigh's method, I need to compute this Kij and Mij, they do not require functions beyond second derivative. So, trial functions need not have we are happy to use trial functions which have only second order derivatives exist. Okay. So, this is the requirement. Whereas, in least squares and collocation, trial functions need to be comparison functions. Okay. You can verify that you need derivatives up to the fourth order. In Galerkin, the trial functions need to be comparison functions. We will see some of this. Now, there is yet another approach which is slightly different from what we have been discussing, that is known as assumed mode method that employs Lagrange equation. This is slightly different. So, again let us consider for purpose of illustration the free vibration problem of an inhomogeneous beam. So, we have the field equation and appropriate boundary conditions and initial conditions. So, we have seen that solution of this differential equation is equivalent to minimizing this functional. Okay. This we have seen, this is Hamilton's principle. So, the idea of this assumed mode method is to approach the problem of minimizing the action integral at the stage of developing the approximation. That means, I will not develop this partial differential equation, but I will develop an approximate method based on the minimization of action integral itself. So, what does that mean? That means, approximate solution can be developed either by addressing the field equation or by optimizing the action integral. So, either we can adopt this or this. So, for purpose of illustration, suppose if I take a beam like simply supported beam, the approximate solution is let us take it to be n equal to 1 to a n of t phi n of x, where a n of t is set of unknown generalized coordinates and phi n of x are known trial functions taken to satisfy all the boundary conditions. Say for example, phi n of x is sin n pi x by L. Now, this is the expression for kinetic energy, this is the expression for potential energy. So, now I will form the Lagrangian for this is this in terms of these generalized coordinates and their derivatives, and on this I will apply the Lagrange equation n number of times. Okay. If I do this, this is simple calculation, we can get the mass and the stiffness elements of mass and stiffness coefficients, and we can get the equation ma double dot plus ka equal to 0 with certain initial conditions. This Kij, that is k n k, is ei phi n double prime phi k double prime, which is symmetric in this case. Similarly, if you look at m n k, it is symmetric. So, this is similar to what we got in Galerkin's method. So, we can see here in this case m and k are n by n matrices, and these are the generalized coordinates with n degrees of freedom. Both m and k are symmetric, Actually, we can show that M is positive definite and K is positive semi definite. One of the limitations of all the approaches including this one is that these generalized coordinates, this vector of generalized coordinate does not have direct physical meaning. Okay. They need to be substituted into a series expansion and evaluate that series, then only it emerges as a quantity in which we can quantity to which we can assign a physical meaning like displacement or velocity, things like that. Now, clearly this M and K depend on choice of these trial functions. So, again in this approach also a partial differential equation governing the behavior of a continuous system has been replaced by an equivalent set of ODEs with a view to obtain approximate solution. Now, in discussion of variational approaches to solution of partial differential equations, there is the set of terminologies that we should become now familiar. I will introduce them now. We talk about what is known as strong form or a weighted residual form and a weak form of the governing equations. So, what they are? Now, the discussion on these forms of equation is basically in the context of finding approximate solution in this form V of x is n equal to 1 a n phi n of x. It is in this context that we talk about these different forms. In the strong form we use the field equation itself, that means we write the governing partial differential equation and want to develop the approximate solution starting from this. Okay. So, this field equation plus appropriate geometric and natural boundary conditions is used to develop approximations based on strong form. In the weighted residual form, what we do is operationally what we do, f of x is taken to this side and we multiply by a weight function and demand that this integral is 0 So, this is like virtual displacement in structural mechanics problems. Okay. So, I will come to that in due course. So, the idea is we can select a set of n weight functions and obtain governing equations for the unknowns a n of t, a n. In this case I am considering a static problem, it is a n's only. So, the trial function phi n of x here, if you are using this method, you see in this method you would need v differentiated 4 times, that means you need d4 phi n by dx4. Okay. Whereas w of x there is no such requirement, it can be it should be integrable, but there is no requirements on its derivatives. Now, in weak form what we do is we carry out integration by parts of this weighted residual statement and see if I can pass on some demands on differentiability of these trial functions to the weight function. What does that mean? Suppose let us do that integration by parts. I get you do integration by parts twice and I get here, if you carefully see, one of the term is w double prime x e I of x v double prime, this is p v prime w prime k v w minus f of x into w of x dx equal to 0 plus these boundary terms. Now, we know that e I v double prime prime is nothing but the shear force, I can call it as F2. So, this is W of L, this is W is here and this is shear force W of 0, bending moment at the support into W1 prime of L and this plus this. This equation is known as the weak form of the governing equation. Now, in this case if you carefully see, the demand on differentiability of trial function is only up to the second order now. The original equation was fourth order, now trial function need to be differentiable only up to the second order, but the weight function now need to possess derivatives up to second order. That means the demands on differentiability on v of x, the trial functions, has been weakened and that has been passed on to the weight function. In that sense it is a weak form, that means demand and continuity goes down on the trial functions. So, for purpose of illustration let us consider the beam be simply supported at x equal to 0 and x equal to L and it be subjected to bending moments m1 and m2. So, the weak form of this equation is this. Now, m1 and m2 are the applied bending moments. So, they will substitute now for that is m1 and m2 will appear there but now the beam is simply supported. Therefore, what I will do is I will demand that this W of L and W of 0, which is the weight function, must be 0 at x equal to 0 and x equal to L. So, if I do that, I will get the weak form in this. Okay. So, that means the inhomogeneous boundary conditions now explicitly appear in the weak form. So, now we have to select phi of x and weight functions so that V of 0 is 0, V of L is 0, because that is a geometric boundary conditions, because it is a simply supported beam at x equal to 0 and x equal to L, and this weight function also need to, we take that this weight function also need to satisfy this. It need not, this need not be 0, therefore, this condition will also be satisfied. Okay. So, again let me emphasize that the trial functions are here in this approximation need to be differentiable only up to the order 2, whereas in the weighted residual form they need to be differentiable up to order 4, whereas there was no demand on weight function. But here the demand on differentiability of trial function and weight function are balanced. Okay. So, this is the advantage of the method. So, if trial functions need to be only differentiable up to the second order, the pool of functions from which we can select the trial function becomes very large, as compared to those functions which need to be differentiated up to fourth order. Okay. That is the main advantage of this method. So, now there are some certain other terminologies that we should be aware of. So, if we go back to the problem of beam on elastic foundation carrying axial load, I think this is a beam carrying axial loads, we got these two terms in the variational form. So, the coefficients of weight function we call them as secondary variables. Okay. The coefficient of W of x is this, and this is declared as a secondary variable. The primary variable V is written in the same form as what is appearing here, that is W of L means V of L. This is a primary variable. Okay. So, in this case, for example, this will be the secondary variable, this is a primary variable. Similarly, at the other end, the bending moment becomes a secondary variable, the primary variable is the slope, right, because this is the function that multiplies the gradient of the weight function. So, that coefficient of weight function or its derivative are called secondary variable. This is the primary variable is in the same form as what the weight function appears, but W is replaced by V. So, this is the classification. So, that means the dependent variable expressed in the same form as the weight function appearing in the boundary term is known as primary variable. Now, coefficients of weight functions are called secondary variable. So, we will make now a few remarks. The weighted residual statement, in the weighted residual statement, as I already said, the trial functions phi n of x must be differentiable up to the fourth order. W of x on the other hand, which is the weight function, can be any integrable function. So, equations for the undetermined coefficients can be obtained by choosing a set of n weight functions. So, weight functions come from a very large pool, whereas trial functions come from a very small pool, a relatively smaller pool. In the weak form, on the other hand, we distribute the requirements on differentiability evenly between weight function and the trial function. Thus, the continuity requirements on the trial functions is weakened, and hence the name weak form. We have a larger pool of functions to select from for the trial functions in this case. The trial functions therefore need to satisfy only the geometric boundary conditions, as the natural boundary conditions are included in the weak form. For example, I got a bending moment term that appeared explicitly in the weak form, right. So, and also we talked about primary and secondary variables, we will talk about this again in a later part of the course. The number of primary and secondary variables are the same whenever we consider even ordered partial differential equations, which often is what we do. They appear in pairs, for example, translation and shear force, slope and bending moment, and so on and so forth. Only one item in each pair can be specified at the boundary. For example, at the simply supported end, we can specify displacement to be 0. We cannot say displacement and shear force to assume certain values, that is not on. Similarly, if you talk about slope, bending moment is 0 and you cannot say slope is also 0. Okay. So, only one item in each pair can be specified at the boundary. Now, in the methods that we have discussed so far, one of the common features that we have seen is that the trial functions are valid over the entire domain of the structure being studied. That means, these are globally valid shape functions or trial functions. This is okay if you are talking about simple geometries like line elements that we are considering, but for more complicated problems it is not easy to construct global trial functions. One more difficulty that we have is the generalized coordinates a n of t, they do not have direct physical meaning. Unless I substitute in this series and sum it up, I would not know, only then I would arrive at a physically meaningful quantity. If I say a3 of t is at some time instant point not 2, it does not specify much, you know, it is a, we cannot interpret directly in any useful way. So, we would like to deal with not simply line elements, we would like to deal with trusses like this, frames like this, and you can imagine constructing global trial function for a truss like this would not be easy, it will be impossible. Similarly, constructing a trial function for a much less you know much more modest structure like this also is not easy. So, in the next class we will see how we can address these limitations, and we will start talking about the development of finite element method, which aims to overcome the difficulties that I just mentioned. So, with this we will conclude this lecture.